Well, let's take a look at this last lesson of the year. We're going to learn a way that we can prove certain ideas generally involving series and sequences, and it's through this new type of proof by induction. Now, let's take a moment and look at the technical college definition you would see in a college book of what proof by induction is. It says, the principle of mathematical induction. Let P sub n be a statement involving the positive integer n. So n is usually 1. 1, 2, 3, 4, 5. If P sub 1 is true, if the very first thing is true, and for every positive integer k, the truth of P sub k implies the truth of P sub k plus 1, then that statement P sub n has to be true for all positive integers n. And that is a really interesting logical vehicle through which we can prove certain ideas, certain things about sequences and series. Now, I know you're looking at that and you're right now you're thinking, what on earth is he talking about? I don't know what's going on. It's the end of the year. Don't make me do this. But let's break it down. Let's make it easier to understand. Here we go. We're going to just take this and break this down into 4 basic steps. The way you do an induction proof is really just 4 steps. Step 1, show that the rule, whatever it is you're trying to prove, show that it works for the very first case. Generally, n equals 1. Step 2, just assume the rule is going to work at some eventual case where n is just some integer later on, k. And this will make sense when we look at an example. Step 3, show that the k plus 1 term also has to work. So by the time you get to step 3, step 1, you've shown it works for the very first term. Step 2, we're going to assume it works for some eventual kth term. Step 3, show that the next term after k, the k plus 1 term, has to work. And the reason why this is working is, look, it's like dominoes. If we establish that the first domino is going to fall, and we can say, then, look, if the first domino falls, and I can show you that the very next domino following a domino that fell will also fall, doesn't that mean that if we push the first one over, we know that the next one, the k plus 1, the second one is going to fall? And if the second one falls, doesn't this show that the third one will fall? And if the third falls, this shows that the next one has to fall. And so we've shown that the subsequent dominoes will all fall if the first one falls, which we've already shown. And then the 4th step in an induction proof is you simply state, by mathematical induction, blah, 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 whatever it is you're trying to prove. Let's do a problem together. So we have this problem right here in your guided notes, right there. And let's work through it step by step, the 4 steps in an induction proof. So what are we saying up here? We're saying if I take 1 plus 3, which is 4, plus 5, which is 9, plus 7, which is 16, and I keep adding, it looks like odd numbers, and I get up to 2 times n minus 1, that's going to be n squared. Now you may recognize this because we actually talked about this in class. But let's see if we can prove it through this system called induction. Step 1, we're going to show it works for the very first case. So sometimes it helps to label these terms. This is my first term, this is my second, this is my third, this is my fourth, this is my nth. I want to show it works, that this rule is going to work for the very first term, which is 1. So is 1, is it equal to, I have to show this, 1 squared, because n is 1. The first term, 1, is that equal to 1 squared? And, you know, do the math. Is 1 equal to 1? Yes, it is. Step 1, I mean, look at the picture I associate with step 1. It's pretty easy. You have to show that it works for the very first case. That the very first case right here, that this is going to meet this requirement. That the first number 1 is equal to the first term squared. And that totally was true. It worked out. Yay. All right, now, step 1, done. Pretty easy. Step 2, it's kind of even easier. We just have to assume that this rule that we laid out up here is going to be true when we replace the n with some future integer we'll just call k. So I don't want to use n again because that's kind of the generic rule. I want to show it, just assume it works for a very specific number k. How do you do that? Well, you just replace the n with a k. 2n minus 1 became 2k minus 1. N squared became k squared. That's it. If step 1 was easy, step 2, I mean, geez, it's super easy. And then we get to step 3. We have to show that if we assume that n equals k, if we assume this statement in hot pink is true, we have to show that the very next term, the k plus 1 term, also is true. Now, let me rephrase that. What we need to show is that if I put in 1 plus 3 plus 5 plus 7 plus ... plus 2k minus 1 right here, if I add one extra term, the k plus 1 term, which would look like this, it'd be 2 times, now I've replaced k with k plus 1 minus 1. That would be my k plus 1th term. This is my kth term. This is my k plus 1th term. I've got to show that that's going to equal k plus 1 squared. This shows it works for the k term. This is what the k plus 1 term would look like. So I've got to show that the black side matches the red side. Now, this is where we're going to do our work. Look at this little guy. We're going to be really working hard here. How do we do this? Well, the first thing we're going to do is we're going to just take the left side, the black side, and try to transform it so it looks exactly like the right side, the red side. I'm not going to touch the red side. I'm just going to play around with the black side and see if I can algebraically manipulate it to look like the red side. So let's do that. Here we go. All right, wait a minute here. Whoa, what? Do you recognize this? Wait a minute. Isn't this first part of the black side just this hot pink expression here? So I could rewrite the entire left side using that hot pink expression. And what do I know about that hot pink expression? Well, this hot pink thing here, this 1 plus 3 plus 5 plus 7 plus ... plus 2k minus 1, we've already established that that's k squared, isn't it? So I can basically just replace this entire expression here with where's my little pointer? With, wait a minute. There we go. Sorry. I could replace this entire expression here with k squared. This whole thing can be replaced with k squared. Now don't forget we still have this black 2k plus 1 right there. So remember, our goal is we're trying to transform the black side into the red side. So coming down here, we have this expression. Wait a minute, this expression can be factored. Isn't that just k plus 1 times k plus 1? And couldn't we write k plus 1 times k plus 1 as k plus 1 squared? Did we do it? Yes, we did. Look, they're the exact same. Wow! So this means that we can now go to step 4, and step 4 is simply where we say, thus, by mathematical induction, and we go all the way back up here and we just repeat the initial proposal, and that is that 1 plus 3 plus 5 plus 7 plus blah 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 plus 2n minus 1 is equal to n squared. And if you want to be fancy and rephrase that, we're really saying, therefore, by mathematical induction, the sum of the first n odd integers will always be n squared. So it's not a quick process, but it's kind of a fun one. Let's do another. Let's do another. Example 2. Now, this is in your notes, so follow along. Let's go through our 4 steps. Remember, step 1, we have to show it works for the first case. Now, this right here is the first case. My first term is 1. And I've got to show that 1, this number 1 right here, can be determined using this generator over here. So is 1, is it equal to 2 to the first minus 1? N being the first term, my first term being 1. Well, yes it is. We can do the math. Is 1 equal to 2 minus 1? Is 1 equal to 1? Yes it is. First term, pretty easy. Second term, or second step, even easier. Just assume that this whole statement we have up at the top is going to be true when we replace the n, the generic n, with a very specific k. So I just rewrite it, replacing every n with a k. Now step 3, this is where we're going to have to work. We have to show that this is going to work when we go one step further. When we go not to the k step, but to the k plus 1 step. So really, what we have to show is that if I add one more term, if I add this extra 2 to the k plus 1 minus 1, see how I replace k with k plus 1, that has to equal 2 to the k plus 1 minus 1 over here. So be careful. Remember, some of these are exponents, some of these are not. Now, how do we show this? Well, again, if you look, this first part right here, this first part, that is the pink part that we know is true because we assumed it has to be true. So this 2 to the k plus 1 minus 1, I think when we add these up, it's just 2 to the k. The 1 and the minus 1 cancel. But this whole thing right here, this whole 1 plus 2 plus 4 plus blah, 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 we know that that is 2k minus 1. So now my job is simply to take this stuff right here and make it look like that. So the first thing I'm going to do is I'm going to put my numbers rearranged. I'm going to put this as 2 to the k, that stayed, plus this 2 to the k minus 1. Now, let's do a little bit of, basic math. If I have one blob and I add another blob, that gives me 2 of those blobs, minus 1. Now, let's look. You notice that these bases are the same? Do you notice that this is 2 to the first times 2 to the k minus 1? Look at what we're trying to get at. And so if I do the math here, let's see, I have the same bases. So the rule is I add those exponents. Did we? We did. Look, we made it match. And so we can end this proof in step 4 with this statement. Hence, through mathematical induction, the original hypothesis is indeed true. Now, you'll notice one of the tricks that we've used in induction. One of the things we've done quite a bit is we've used step 2. We've made the replacement. We've replaced the first part of our induction statement. Right here, we've replaced the first part with its simplified version, and then we've used that simplified version to move forward. Now there's one more example. We're not going to be able to finish it together, but it's this. You may recognize this as Gauss's little trick, but I want you to slowly walk through these 4 steps. Try this on your own, and we'll do some problems together in class. Best of luck to you.